Mathematics definitely does get quite funky, especially when we start seeing these fancy Greek letters flying about. Um, we're going to have a look at what exactly these Greek letters can mean, and we're going to see what sort of problems we can solve with them. I'm Daniel from CMC Learning, and I say we get stuck in. So, sigma notation. Essentially, sigma is can be represented by this Greek letter, this large E, if you will. We call this capital sigma. So the capitalized version, as if we have letters like A and A, or capital A. We say that the sigma on the left is capital sigma. And mathematicians decide to use this for a very special function, in which case we can use them to define sums. So I can have something like this. Let's look at the most sort of trivial form, I say. If we have a look at what we're working with, we have essentially what this is saying: the sum, when r is equal to 1, of r until r is equal to 5. So it's very important to understand what everything is. So, as we said, the bottom of this sum, this sigma, essentially tells you what your starting value of whatever is in your sum should be. You then have what we call the argument of the sum. If you will, you could put it in brackets. This is the term that is being summed however many times. That number of times is dictated by the number that we put on top of this capital sigma. That tells us essentially up to what value of r should we stop. So let's write this out explicitly, which is the best way to tackle all of these sigma notation problems, and let's see what we get. So with r is equal to 1, we have 1. The next term is then when r is equal to 2. So when r is equal to 2, we just have 2. We replace it in that sigma. When r is equal to 3, we get 3. I'm sure you see where this is going. And the important thing is we do that until we've reached the value of r given by the top. So if we were to write these explicitly, we have r is equal to 1, 2, 3, 4, and 5. And this would be our sum. We just add up all of these numbers, and what we get here, we get 15, I believe. In this case, we get 15. So that's the sum of r from r equals to 1 to r is equal to 5. But some of these questions can look a little bit more complicated. And there are two sort of types, or two specific layouts that we should be on the lookout for. Specifically the one we looked at just above. So let's say this was 15. We can get some sort of complicated numbers going here. One of the forms that we should be on the lookout is something, or that we should be on the lookout for, something like this. So let's again read out what we're saying, or what this essentially mathematical term is saying. We need to do the sum of 3r minus 2 for values of r ranging from r is equal to 1 all the way up to values of r equals 15. So again, let's write out the first few terms and see what we get. So when r is equal to 1, let's look at what this first term would be. So that would be 3 minus 2. We just get 1. When r is equal to 2, let's have a look at what we get. We get 3 multiplied by 2, so 6 minus 2 gives us 4. When r is equal to 3, we have 3 multiplied by 3, 9. 9 minus 2 is 7. And so on and so forth. We can index these terms as such, just like we did above. And let's now have a look at what's happening. So we could write out all 15 terms of the sum, and we'd be here forever. Some questions have values even higher than 15. Or we could recognize sort of the subtopic that this is representing, or the topic that this is representing. Here we should be thinking about series and sequences. Just by looking at these terms here, we can notice that we're increasing values by a certain difference, if you will. In this case, we have a difference of 3, and hopefully we can recognize that this takes the same form as an arithmetic series, where the first term is equal to 1, the common difference is equal to 3. In this case, we need to be careful. So how many terms are we summing? Say that we're summing up to 15 terms, aren't we? There are going to be 15 terms in this series. So instead of writing our answer in sigma notation, which is often easier to do if you were first writing down something on a page, you need to know what the sum of something is. You'll write something like this down, but then we want to simplify it. So we can use our sum to n terms for an arithmetic series and see if it can help us with the answer to this. So here we go. We can just sub in these numbers over here and see what we get. We can say that the sum to 15 terms is equal to 15 divided by 2, multiplied by 2, multiplied by the first term. In this case, we get 2 plus 15 minus 1, 14, multiplied by 3. And this is something we can just pop into our calculator and see what we get. In this case, we get 330. Just by looking at this number, you can probably tell it would be quite difficult to add up 15 of these terms all together just to get to 330. And hopefully we've seen that there's a certain term here, or a certain format of terms in the argument of this sum that are quite useful to us. We can see that when we have a linear term of r, so 3 multiplied by r minus 2, we end up with an arithmetic series. So that is definitely something to be on the lookout for. Whenever we have a linear term here, it's obviously not inherently obvious what we have, but once we write out the first few terms, it becomes quite simple. The next sort of terms that we should be looking for, and again, it's also good to know that this argument can take any number of terms. So it could be k, it could be a, it could be x, for example. Let's have a look at something like this. So 3 multiplied by minus 2 to the power of k. Well, as always, we can write out the first few terms. Perhaps it is important to put this sum going from 1. Or let's try this variation. Just k is equal to 1. That'll give us a nice sort of first term. So let's have a look. We're going to do 3 multiplied by minus 2 to the power of 1. That will be our first term. So 3 multiplied by minus 2, essentially, is just going to give us minus 6 for our first term. Let's look at the second term. Minus 2 to the power of 2. It's going to give us 4. 4 multiplied by 3. Well, that's going to give us 12. It's going to give us a positive 12. That's the important part. So now have a look at the third term. We're going to get negative 8. Negative 8 multiplied by 3. Well, that's negative 24. Just by writing out the first few terms as we did above, we can hopefully see a pattern emerging. So let's have a look. We can see that our first term is then doubled, but then multiplied by minus 1. And we can see that that process happens again. So in a way, we're multiplying by minus 2 with each term. And hopefully that should also jog our memory, because what we have here is a geometric series. So a series where there is a common factor between each of these terms. So in this case, we have minus 2. So again, just by writing out the first few terms, we've managed to almost trivialize this problem. Here we can say that a is equal to, well, first let's write out what this sum to n terms for a geometric series is. R to the power of n minus 1, or divided by r minus 1. This is a common way to write it. We also have a to the 1 minus r to the n divided by 1 minus r. We do have a video explaining why there are two equations here. I would definitely recommend checking them out if you don't inherently see why these two are identical. But we'll press on and sub in these values of a and see what we get. All the values of a, values of r, and values of n. We can see that a is equal to minus 6, r is equal to minus 2, so there's common difference. And then n, well, we're summing 20 terms. So let's have a look at where that gets us. So minus 6 multiplied by 1 minus minus 2. It's very important to utilize brackets here, in my opinion. Keeps all the terms independent, especially with all the minuses. And then we're doing 1 minus minus 2. We could just simplify this to 3, can't we? Mind you, we are using this form of the expression, or of the sum. And putting this into our calculator, we can figure out what this sum is. Essentially, as said before, trivializing what would have been a very sort of long-winded process of adding these terms, 20 terms, and seeing what we get. Well, from here, we end up with this number over here, quite large, 2 million, 2.1 million. So you can imagine adding up all these terms. Getting to 2.1 million is quite tricky. So yeah, here are two examples of things to look out for. In the second one, we should note that when we have something to the power of the index being summed, we end up with a geometric series. And when we have a linear relationship with the sort of term being summed, the variable being summed, then we have an arithmetic series. So these are two things to look out for. And while these numbers can be sort of in a way misleadingly simple, you could get examples where you're only summing to, for example, 8 or 10 terms. It is always going to be quicker to see if you can utilize some of these equations. So I hoped this was a nice introduction to sigma notation. There are definitely some trickier problems that I do recommend all of you to try out. If you have any questions or problems with anything we covered today, do let us know in the comments below and we'll be sure to get to them. Anyways, thanks for watching and we'll see you in the next video.